Good morning, everybody. I'm sorry, are the Lakers doing something? Is that where we're... No, we just can't.
They're up 3-1 right now.
Okay. Okay. So I don't follow basketball at all, so.
What do you watch?
YouTube. In terms of sport,
Yeah.
if I'm going to watch something, it's going to be one of two things. It's either going to be the Olympics every 2 years, or you could probably rope me into watching climbing competitions. The world circuit climbing competitions. If soccer's on, I'll kind of sit there and watch it, but after about 5 minutes, I get bored. A lot of watching sports bores me. Doing sports, okay. Watching sports. We're not here to talk about Mr. Balogh's sport life. What are your questions? I just saw the Lakers tonight. My father-in-law's really into it, so you gotta help me out, right? I'll be talking.
It's time you're a Laker fan.
He wouldn't mind that. He's from LA.
Tell him that Curry is the GOAT over LeBron.
Okay, I should say that, and then yeah.
Especially if you come back and win.
All right, what are your questions for this exam?
Statics.
Bernoulli?
How do we know when the height is insignificant?
There'll usually be some language, so the question is, how do you know when the height's insignificant, right? So there'll usually be some language in the problem that says either it's a straight level pipe, right? But anytime the water has to go from a higher point to a lower point, you gotta have height in there somehow, right? So look for no change in the actual height of like where the fluid is going, if that makes any sense. It can be a little bit tricky.
Like on number 10, where they give us two heights, but we only use the little.
So we're talking about
From the homework.
from the homework, which I actually had pulled up somewhere around here. There it is. You said number 10? Okay, so just looking at the problem, only little d is going to matter. Unless they ask me what the pressure is at the very bottom of the reservoir or something. Only little d is the one that's going to cause any kind of motion of the fluid. The fluid down here isn't going to do anything. Remember, pressure is only dependent on the depth or height of the water column that's there, right? So does this problem ask us how fast is it going or something? Okay, frictional force and then how much volume. So to find out like the volume of water that comes out of here, I need to know how fast it's going. What's the answer? Square root of 2g, in this case little d. Right. So it's just that little d that makes that difference. Did I answer your question?
Yeah, I just like, how do you know?
How do I know that?
I was doing all kinds of stuff to try to find it. Like I took the difference in them.
So the difference between the two D's right here would be like this part of the reservoir, and that part's not doing anything. I guess it goes back to pressure and the fact that pressure only depends on how deep you are into the water. And since that outlet right there is only that deep, I can ignore, like remember, it's not total amount of water in the reservoir or volume, right, any of that kind of stuff, how deep the reservoir is. All that matters is how deep. So how do you know? I just told you. Because sometimes people are like, how do you know so much, Mr. Balogh? Like, well, knowing is how you know stuff. Like sometimes you just need to be told, right? When I did that siphon, right, with the tube coming out, you saw how it was only how far below the surface of the water it was. Like I could like hold it midway in that water, right? And as I went down, it still went faster. Like it was only had to do with surface to where the end of that tube was, that vertical height. As to why pressure only depends on that. It's the weight of the fluid above you that's pushing down on you. The stuff that's below you is holding you up. I don't know if that helps. That would probably getting too deep, right?
Yeah.
Pun intended. Yeah.
For the same question, can you explain why we don't use atmospheric pressure on top too with the fluid pressure?
Yeah, so in solving this problem, you do have to kind of take a look at sort of the net force that's acting on that stopper. So atmospheric pressure, the pressure in the water right there. I should stop pointing at the screen. I should actually write on the screen. So you have atmospheric pressure up here. And that atmospheric pressure plus the rho GD to get to this level would be the total pressure acting on that thing right there. However, what's on the outside of that stopper? Atmospheric pressure, right? And so when we look at the sort of the free body diagram, right, you've got the force from atmospheric pressure pushing in, you've got the force from the water, right, this pushing, but this force is the result of both the atmospheric pressure plus the rho GD times the area right there, right? So you end up, these end up canceling each other out. Atmospheric pressure is pushing on both sides.
Thank you.
And all that matters is the pressure from the water. Any questions?
Can you explain static extent?
Not really. Try to avoid it.
Like the torque equation, I think those are dead.
Right, it's the torque equation that's really the problem, isn't it?
Yeah.
Okay, so let's break that down again. Make sure that we're all on the same page, as it were. Torque, right? What is a torque? How do we find torques? How did I teach you to do it? That's not a good sign. It's R and F, right? Perpendicular to each other. Now, technically, you can do R sine theta, but it's more useful in solving statics problems to have the two methods of either finding a perpendicular component of force or finding the perpendicular distance. But either way, when you have a, let's say, I don't know, let's say this thing has weight pulling it down and some sort of tension holding it up right there, and it's pinned down over here, right? Okay. So when we start this torque equation, right, when we set all the torques equal to 0, you have to define an axis. You can't talk about torque without having some axis of rotation, and then that axis sets out all of your distances. So if I choose this as my axis, then my distance to the weight, okay, is going to be, well, maybe it's half the length. Okay. Now, because of the way this object is being held, are those two forces, is the distance L over 2 and the force that's being applied, mg, are they perpendicular to each other? Yeah. Okay. One's horizontal, one's vertical. So I can go ahead and just write that torque, right, the torque due to mg, as the distance L over 2 times the force, and I'm good to go. All right, so if I call that a positive torque, that means that I'm specifying that clockwise is positive. All right, what about T? What if T is attached at a distance of L over 4? So are T and L over 4, are those two things perpendicular to each other? No, one, you know, the T is at some sort of angle, isn't it? So maybe, because engineers are weird, maybe they measure this angle. Okay? So now, what do? We can either find the perpendicular component of force to that distance, or the opposite. We can find the perpendicular distance to the line of action of the force. Both of them will give you the same answer. Visually, conceptually, I would latch straight on to just get the perpendicular component of the force. We've got this length that's going horizontal. I need to find a perpendicular component. It's literally just sitting right here, this ty, right? If I break t up into two different parts, tx and ty, and I can see that my angle is touching. So ty is going to be t cosine theta. That's my perpendicular component. And so now I can go ahead and write minus the distance, L over 4 times my force, t cosine theta. And this is why I don't like using or teaching you to use RF sine theta, the way that the book teaches. Okay? Notice, because of where the angle is given in this problem, we ended up with a cosine theta in it. You will be far more successful and make fewer mistakes if you are constantly thinking about perpendicular, right? Getting things to be 90 degrees to each other. Whatever angle they give you, right? Find the perpendicular piece. So the other way to do this one, and it can be, I don't know, maybe a little bit more difficult to see in a horizontal problem. So sometimes I hesitate to do it, but we're going to do it anyway. I'm just recreating it. So here's t. Here's my axis. We know that this distance right here is L over 4. And if we do the line of action of the force, okay, what we are looking for is a distance that is perpendicular to t. That distance always starts from the axis and goes somewhere. So the distance I'm going to find is that perpendicular distance right there. I draw a perpendicular line from the axis up to t. And it's got to be this distance that I'm trying to find now. What is this new distance? That side of that triangle right there? That's what I need to find. That's the perpendicular distance to the line of action of the force. So now I have a triangle. I can recreate my triangle. It's a right triangle right there. I'm looking for that side D. I know that this is L over 4. And in terms of the angle given, well, this can be screwy. If they gave me that angle right there, then that's going to be this angle right here. How do I know? What's the angle in there? It's 90 minus theta, isn't it? And so what does the other angle, the right triangle, have to be? 90 minus theta, so it's 90 minus 90 minus theta. Which gets you back to theta, right? So I've got this angle, theta, I've got the hypotenuse, and is D touching or not touching that angle? It's touching the angle. So it's going to be, so D is going to be equal to L over 4 cosine theta. And so when I come up here, I would write down L over 4 cosine theta as my distance, and then for my force, I would just write down T. And you get, again, you get exactly the same mathematical expression. Because the idea of finding a perpendicular component of force to some distance that you draw, and the idea of finding the perpendicular distance to the force are the same thing. But visually, conceptually, it comes from two very different directions. Okay? So when you are doing these torques, you've got to remember your direction, positive or negative. And I taught you the pencil trick, right? Okay. You're allowed to do during the exam. Just don't hold it way above the divider, right? Keep it to yourself. Remember your directions. Remember And then once you have your directions, get in and find out what the nitty-gritties are. But I strongly suggest you break up the steps to do that. Don't try to do that all at once. Because if you try to get the direction and the perpendicularness and how many torques there are on the problem, you try to do that all at once, you might be thinking to yourself, oh, I'm saving time by doing it all at once. No, you are wasting time because you're going to make mistakes and then you got to go spend time to fix those mistakes. Break that up. How many torques are there? Where that depends on where I put my axis, right? So pick your axis, find out how many torques you got. Don't worry about what they are, just figure out whether they're positive or negative. And then once you have that all laid out, then start breaking it up into finding perpendicular things. Did I answer your question? Okay. It's something that comes, I think, with a lot of practice, unfortunately, right? And there's one thing in this semester we never really have all that much time for is practice. And I know you're sitting there going, Mr. Balogh, I've done plenty of practice, right? I do 20 to 30 hours of homework in this class. I'm like, yeah, it's not enough. like it's just seriously, it's just, physics is one of those things where the more time you put into it, the bigger the dividends are.
Can you go over Torricelli's theorem? Oops. I think it's, I'm not sure if I'm saying it right, but it's Torricelli.
No idea who that is. Is that in the book? Bernoulli? No, you're starting with a T, aren't you?
Yeah.
I have no idea what that is. That wasn't in the homework I gave you.
I think it was part of the chapter 14.
Yeah, some ancient Italian. There's always Italian guys with the fluid things. I don't know what it is, but a lot of fluid stuff going on. It must be all that pasta, you're right? They sit there and stare at the water. I'm making fun of my ancestors now. Torcelli, it just does not ring a bell. Obviously, you're not going to need to worry about it for the exam. But.
It has to do with the opening, like in a tank. The lower it is, I think, to the surface.
Faster it goes?
Yeah, the faster.
Well, yeah, that's just conservation of energy, so square root of 2gh. Maybe Torcelli, maybe that's what made him famous, was square root of 2gh. Pascal's principle, Archimedes' principle, Bernoulli's principle. Those are the three main tenets of fluid physics. I think a fluid dynamicist would disagree with me, but they're not here, so I'm just going to stick with that.
I have a question about statics, actually. If you put your, let's say you made your point of zero in the middle of the system, and if tension was all the way on the right side of the bar, my only question
So,
is,
like, we do tension over here.
yeah, and say for some reason you picked your point as in the middle. So if one of those is a negative torque and the radius also negative, it turns out to be positive, right?
No, because the distance is just a distance.
Okay.
So it's a good question, right? So
So just,
we can break the h vector up like that. We can break the t vector up like this, right? This one and this one don't cause torques because they would be parallel to any distances we could draw here, right?
Yeah.
And you're right. Technically, those distances are vectors.
Yeah, that's
But one of the things, right? When I taught you to do this, I never wrote a vector symbol over the top because we're always going to handle our direction as a clockwise or counterclockwise. Okay. So to answer your question, though, if I do R crossed into F on this side, the TX, right? My thumb is pointing out of the screen. Okay. If I come over here and I do R, F, which way is my thumb pointing? They're in opposition to each other. So we could go through the formalism of doing all that. If you were all physics majors, that would be all that we do all day long. okay? But you're not, you're engineering major. I'm trying to teach application, right? So the application of this is you grab your pencil and grab it in the middle, that one goes up, okay, that rotates counterclockwise, okay, this one rotates clockwise. They're opposites to each other, so we'll just make sure we get a minus sign in there.
Okay.
But it works out whether you do it the vector way or not.
Okay. Alright. Thank you.
Mm-hmm. Yeah, there's a lot of behind the scenes and under the hood stuff that I don't talk about.
So I'm just going through the book.
You're welcome, by the way, for that.
Yeah.
There are some physics teachers that think it's their sworn duty to do like a core dump every lecture, right? And just spout off as much information as they possibly can, and it doesn't help students at all. Yeah, like Torch. No. Maybe I should know who Tortelli is. If he came up with square root of 2gh, he's my hero.
Can you go back to the details page?
I can try.
Why is the second part negative if we're doing it this way, the t?
Second part where?
L over R, t cosine theta?
L over 4.
Yeah, because if you're doing it this way, t is,
I defined clockwise as positive.
okay,
You see that?
right, gotcha.
So, yeah. Remember, that direction is just an arbitrary thing. So if I say clockwise is positive, t is causing a counterclockwise rotation, so I put a minus sign on it. I know you guys always insisted that counterclockwise is positive, which is fine. Fast and loose with, I mean, as long as you're consistent, right? Those two things ended up in opposition. So does it matter if it's L over 2 mg minus L over 4 t cosine theta, or negative L over 2 mg plus L over 4 t cosine? Those are the same things mathematically. John?
Good question. They did a homework problem in chapter 12, and it was with a science problem, but it wasn't exactly perpendicular. It was kind of like tilted upwards at a different angle.
Yeah, I happen to remember the number, do you?
I think it was the last one. Yeah.
Okay.
I was having trouble with that one. I didn't quite understand how it worked.
Well, I can answer part A real quick. The x component of gravity, 0. Right? Like, okay. Oh, and this even says 0, right? I wasn't even reading. It says 0 right there. Y component, so Y component, right, would just be the mass of the beam times G. Did they give me the beam? Just mass? No, so I gotta go find it. Okay. What are the force on the beam from the hinge? So, is your question like, how would I do the free body diagram and the torques?
Yeah.
Okay. So, first of all, if I taught you 2 classifications of statics problems, like all statics problems can be classified in 1 or 2 kinds, right? What kind is this? This is a ladder problem, which immediately causes stress, anxiety, and depression and everything else because ladder problems are harder, right? Just for whatever reason, they're harder. So you take a deep breath, you believe in yourself, or if you can't do that, you believe in me that says that you can do it. And you start. And you go, okay, there's going to be like a pin X and a pin Y. And again, how do you know? Well, knowing is how you know stuff. Whenever there's a pin, draw the X and Y components at the pin. You're going to have to get there eventually anyway, so you might as well just do it. And then we've got the weight of the beam. It says it's uniform beam, so that means its center of gravity is at its center. And then we have this tension in this cable acting over here. All right, so we can do Newton's second law in just linear terms, just writing out the forces in the x direction. I've got t minus px. I'm using their coordinate system that I cleverly drew over with mg. And then in the y direction, it looks like I've got p minus Py minus mg. Okay. Now we're left with not being able to solve anything there. Oh, they did give me the tension in the cable. That's interesting. So what do I know Px is? It's whatever number they gave me, right? Because this equation right here is telling me that Px is equal to T. And then, all right, well that gets me there. I still need Py if I'm going to be able to find mg. And so how am I going to find Py? We are going to go ahead and try to, well, maybe we can just get it from the torque equation. Sometimes when you can't do anything, a lot of times I'll do the forces first, see if I can solve the problem from the forces, and then realize I can't, and I have to go and do torques, and then I'm kind of forced into it kind of thing. So, is the square footage on the diagram? Okay. You're responding to Serge, right?
Yeah, we're trying.
Yeah. I did my best as far as I couldn't find my notes. All right, so we are going to do the torques. Where are we going to put the axis? I'm going to put it down there at the hinge, at the pin. I know I need the pin Y or whatever, or pin X or whatever it is, right? I'm not going to get, I don't want to put the axis anywhere else, right? Put the axis at the point of greatest number of unknowns, right? So that just makes the math simpler, and we'll do some algebra later. So my axis is right there. We'll do your way and go counterclockwise is positive. Okay, so help me out here. How many torques are acting on the beam if the axis is down there? It's 2. What are they? The torque from mg and the torque from the tension. You notice there, I'm just kind of making a list, really, right? I mean, eventually it's going to be an equation, but I'm just, and you can like list them off on the side. Draw yourself a little spreadsheet and like list whatever method works for you. You don't have to do it my way, but I'm trying to model for you ways to not forget different things. Okay, what's the next step? Now that we've got the torque sort of roughly identified how many we've got, what do we do? What's that? Yeah, the directions, whether they're positive or negative according to a rotation. So mg, negative, using the pencil trick. And torque, hopefully is positive. Let's check it. This is like this, right? So I push my, yep, it's rotating counterclockwise, so we'll call that one. Okay, now that I've got that, now that I don't have to think about like their signs anymore or any of that kind of stuff, now I come in with the perpendicularness, right? So, in the case of mg, I'm going to do the line of action of the force. Not only does my brain see it easier, you guys need practice with it, okay? So, we're looking for this distance down here, okay? And that angle theta that they give us is kind of funny. All right, so I've got a triangle that consists of a hypotenuse of the length of this thing divided by 2. My angle theta is over here, and I want this side, the horizontal side of that triangle. So, sine or cosine? Sine. Why is it sine? The angle is not touching that side. If you want to do more geometry, alternate interior angles are equal, right? And it's still not touching, right? Like it just, trust that. It will save you sometime in the future. I still have people email me in graduate school. Mr. Balogh, thank you so much for teaching me touching, not touching. I can do it so much faster than everybody else. You're welcome. It's not a race. All right. So what do I write down for this torque? What's the distance? It's L over 2 sine theta. Where did the minus sign come from? Came from the step above, right? It's just along for the ride. And now I'm writing down a perpendicular distance to a force. What's my force? mg. All right. And then the positive side comes down from the line above. And let's see, I've got this tension right here, right? Okay. And in the case of the tension, my line of action is a horizontal line. I have a length L, the entire length of the thing, which forms a hypotenuse, right? And I need this perpendicular distance right here. I can draw my little triangle up here if I want, recreate it. This is L, this is the distance I need, and the angle right there. Sine or cosine? Cosine. Why is it cosine? Touching the angle. I know physics at a lot of times can feel like you're guessing your way through it. And you're just sort of looking at equations and you're throwing them at the wall like undone pasta, hoping it'll stick. Don't ever do that. Don't throw your uncooked pasta at the wall to see if it's done. Okay? How do you know when your spaghetti is done?
You can taste it, but it looks soft.
Okay, you taste it. There's easier ways, okay, to tell when spaghetti's done. Look at the water. When spaghetti is done, okay, the surface of the noodle will become starchy. Why do you want the surface of your noodle to be starchy? What is the purpose of noodles? To bring sauce to my mouth. That is the whole purpose of a noodle. Calories, whatever, but to bring sauce to my mouth, right? The only way a noodle can do that is if it has a starchy coating, and it will only get a starchy coating when it's done. Now, we'll have it when it's overdone, so don't cook them too far. But yes, you can taste it, but you can look at the water. The water will go from clear to cloudy. And really, at the point where it transitions from kind of being able to see the bottom to not being able to see the bottom, you're within 1 minute of being done. Cooking with Mr. Balogh. So some of my students have demanded that class, and unfortunately, in the state of California, I'm not allowed to teach it because I do not have a master's degree in culinary arts. It's just the minimum qualification, and or industry experience, and I'm not an industry. So, all right. So this is L. What was it we say? Cosine theta. I got distracted. L cosine theta is my distance, and then what's my force? T. Okay, so now that I've written that out in terms of problem solving, like we went not down a rabbit hole, we went along the main path, okay, of the problem. Now we got to step back and say, what are they asking for? Well, they wanted to know the weight of the beam. Are there any equations on the screen? I've got an x, a y, and a torque. Are any of these going to help me get that weight? Yeah, the torque equation is going to help me get that weight, right? Okay. And then I got to go back and sort out. Now that I got the weight, I can find py. Now that I know, then I got all the components, right? And it kind of slots together like a Rubik's Cube puzzle or something like that, right? In a lot of ways, physics at this level, engineering in general, is very algorithmic. You run an algorithm. There's a process, right, that you apply to every situation. I know you think, well, golly, the process is different for every problem. And, you know, my hope beyond hope is that eventually you'll see that, no, the process is actually the same. The details get different. But if you can really believe in that process, it can get you places. Answer your questions on it? Other question? Got another one, Jonathan?
Yeah, I was going to ask, I didn't quite understand
Bernoulli's principle? So not the equation. Bernoulli's principle is that the faster a fluid moves, the lower its internal pressure. Don't confuse that with the pressure that like a fluid moving and like hitting a wall or something. That's different, okay? Internal pressure is internal to the fluid. And so the faster a fluid moves, the lower its internal pressure. And I gave tons of examples of this, right? Vascular flutter, floating the ball above the blower, right? If you have a fast moving stream of air, that's where your low pressure is. If you have a fast moving stream of water, that's where the low pressure is. And I know that you have like this intuition that's telling you that can't be right or that's wrong, because Mr. Balogh, I've used a garden hose. And when you turn the water on, right, before you go and squeeze the trigger at the end, the hose pressures up. Well, okay, that's fluid statics, right? The fluid isn't moving yet, right? When you hit that trigger and the water begins to flow, the pressure inside of that hose does drop. Now there's water pressure on the end of it that keeps pushing the fluid through, right? But as the faster that fluid flows, if you had a nozzle that let you set the speed, you go from slow to high or something like that, right? Then you would see that eventually there would be a speed at which your garden hose would collapse on itself, because the internal pressure of that fluid would reduce so much that the walls will close in. I don't make the rules, I just teach them. Does that help, Jonathan?
Yeah.
Okay. And you said you had a question?
Yeah, about buoyancy, when like an object is by itself and submerged in water.
Mm-hmm.
How do we know that the one that we did in the past?
So like the crown example where you weigh it in air and then you weigh it in. Okay, so the question is about buoyancy and weighing an object in air versus weighing it in some fluid. I'm not sure what your question is. How do we know what? How do we do it? Okay. Let's do a boat. You can tell it's a boat because it has a sail. It's supposed to be a sail. And that's a pirate. Okay. So there's a ship, right? Okay. And that ship, usually ships don't have weight. They have something called displacement. And a ship's displacement is how much weight of water it displaces. Okay? So let's say that this ship displaces 45,000 newtons, typically measured in pounds, or really for larger ships like tons, right? They'll say 2,000 tons of displacement or something like that. We'll just give it that, right? So what this communicates for a ship that's just floating there, right? Okay. If we know the ship has a 45,000 ton displacement, we know what the weight of the ship is. What is it? It's 45,000, because the buoyant force and the weight of the ship have to be exactly equal to each other. Why? It's floating, and floating is statics, right? And statics means that we're not accelerating this thing anywhere, and so therefore all of the forces, whatever they are, have to add up to zero in order for that acceleration to be zero. And so knowing that the displacement is 45,000 newtons, that means that's like the water that was pushed out of the way, the weight of the water that was pushed out of the way, that has to be equal to the weight of the ship. Knowing that that's the displacement, right? Knowing that the buoyant force is equal to that, right? Allows us maybe to then go and calculate the volume of water that got pushed out of the way. Okay? So that's all, I don't know, maybe straightforward. So weighing right, an object that doesn't float, right? So this boat is floating, right? But what if the pirate drops an anchor? You guys are getting the full treatment today. Complete prowess of my graphical ability. That's like peak Mr. Balogh art right there. Okay. Now, that anchor is attached to that rope, right? And what happens if the rope gets cut? I mean, what is the purpose of an anchor? What's an anchor supposed to do? Sink, right? It's supposed to drop down and grab onto something, right? So that the boat doesn't wander away. I probably just offended everybody in the Navy. But anyway, right? That's the whole idea of this anchor, right? Is to keep the ship in one location, or at least approximately one location, because there are currents and that sort of stuff. So that anchor, without that rope, would sink. So if we were to cut the rope, right, what would be bigger? The weight of the anchor or the buoyant force acting on it? Definitely the weight of the anchor, right? This thing is sinking, okay? So in order for it not to sink, there also has to be a tension acting upwards. Again, with the anchor attached to the rope, sitting in the water, it, assuming it's not attached to anything, right, resting on the ground, that anchor has to be held up. Well, there is buoyant force, because does the anchor displace water? Yes. It's just it doesn't displace enough water. So if the anchor has a weight equal to 1,000 newtons, right? But the buoyant force is only equal to 100 newtons. Again, the buoyant force depends on what? The weight of the water that's displaced, the weight of the water that's pushed out of the way. We know the volume of water that's pushed out of the way. What's the volume of water pushed out of the way? What does it have to be equal to? The volume of the anchor, because it's completely surrounded by water. Now, for the boat, is the volume of water displaced equal to the volume of the boat? No, there's way more volume of boat than there is water. Because the only way the volumes can be the same, volume of object and volume of fluid displaced, is for what to be true? Completely submersed or immersed in the liquid. And by definition, a boat that is completely immersed in a fluid is a submarine. As far as I know, no pirates had submarines. So, back to our anchor, right? What do we know the tension is in this rope? It's 900 newtons. How did you do that? I can subtract. You did physics. That's physics right there, okay? Knowing that this all has to add up to 0, you just did vectors in your head. See how far you've come? You're like, Mr. Bailey, this is easy. You can do a homework problem or something, right? Those are hard, right? But the same principles apply. Yes, they get a little bit dirtier and directions make it a little bit different. So when we weigh this anchor in air, we get 1,000 newtons. When we weigh it in the water, weigh it as in terms of like the force, right, of the tension acting on this anchor, the anchor doesn't pull on the rope as much as if the anchor were dangling in air. Because if the anchor were dangling in air, the tension in that rope would be 1,000 newtons. But why is that? Why does air apply a buoyant force? It does, but its density, right, is like, was it 1.29 kilograms per cubic meter? And water is 1,000 Water is 1,000 times more dense, right? The buoyant force acting on things when they're in water is 1,000 times bigger than the buoyant force acting when they're in air. And does a 1,000 Newton anchor care about the buoyant force from air? No, right? It's a matter of scale there, right? It's not that it disappears, it's just it becomes so small that we can kind of go, it doesn't matter. So am I answering your question about how do we like know when something's hanging or submerged and its weights. So there is a difference between an object that wants to sink, that's being held up and being completely immersed in a liquid, and then something like a boat that's floating on top of that liquid. Anything that's floating is always going to displace exactly its own weight. But is the anchor displacing its own weight? No. And so therefore it's going to sink. If the rope is cut.
So if you put the anchor on like a giant ball with like gaps of air,
Uh-huh.
you get it to float eventually?
Yeah. Because the tension will, that ball is providing buoyant forces pulling on a tension, right? Yeah. So you can make a giant ball of iron, okay, with enough holes in it that it would just float there completely submerged in the water. What did I just tell you? What did I just describe? A submarine. A submarine is a big ball of steel and other things, right? That has enough air in it so that it does what? Sometimes to the surface. So how do you get a submarine to go to the surface? Yeah, push more air into it. Well, but isn't a submarine sort of like a fixed volume? Right? Submarines don't act like balloons. Right? Okay. You don't blow a submarine. Right? Okay. No, right? But there are parts of a submarine called ballast tanks that do exactly that. A submarine's ballast tanks are tanks where water gets pushed in and out of the tank. And that water changes the density, the overall density of the submarine. So what I'm trying to tell you is submariners intentionally put holes in their boats to cause them to sink. Because you want the submarine to go under, right? So if you want the submarine to then come back up, you need to be able to push that water out of the tank, which is exactly what they do. It's called blowing the tanks. If you blow the tanks, then all the water goes out and the net density will be less and the buoyant force will be enough to lift the submarine out of the water. Just don't let water into the parts of the submarine that aren't a ballast tank. All right? Key feature. How to operate a submarine. Fish do the same thing. They have bladders inside that they will put fluid into and fluid out of in order to change their buoyancy in the water. Now, we are of course ignoring any propulsive forces because submarines do have basically underwater wings that as the motor of the submarine pushes it forward, those wings provide lift and they can actually drive the submarine to the surface under power if they need to. Fish do the same thing with their fins, right? They can push themselves up. They don't need to sit there and try to get a whole bunch of gas into their bladders before they can. And so why does the sad, dead pet fish always float on the top? The bacteria, the decomposition is putting gas inside of the tissue and upsetting the equilibrium of the fish.
But I definitely had a goldfish that would sleep upside down sometimes.
Well, the sleeping's different.
Okay, but I feel like why would it sleep up? It definitely gave me a heart attack as a kid.
Right, because you're like, right, yeah. So, we need to talk about why your parents let you have it. Anyway, so fish don't care which way is up. They are in zero gravity. I mean, they're not, but they're basically the same thing as an astronaut, right? Because the buoyant force is lifting them up, right? Gravity's pulling them down. It's just completely canceled out, right? We feel that as the floor, but for the fish, it's like which way is up? They can tell lights that way, dark that way, big mouth trying to eat me that way, right? Like they can tell those things, right? But in terms of, long time ago in high school, I was on the scuba diving team. We had a scuba diving team. It was a club, but there were not competitive scuba diving. That's something I'd watch. There weren't competitions in scuba diving. It was more like service projects to go clean up the ocean. Different things, right? So we, as a team, we would go out and do these things. Anyway, we were taught if ever you were like going into a cave or any underwater structure or something, it's really easy to get disoriented when it's dark underwater, like night diving. It's seriously hard to tell which way is up when you have no light cue, because there is no gravitational cue. What's that? Yeah, you watch the bubbles, okay? Or you look at the kelp. Right, okay? So yeah. Yeah, spit or drool or something, right? So that you know which way is the out. There was another hand. Yeah.
So there's a difference between sinking and floating objects, their buoyant force. Can you describe that again?
An object sinking, its weight is bigger than its buoyant force,
Okay.
by definition.
And if it's floating, like in the case of the.
Then the buoyant force is equal to the object's weight. Again, to meet the conditions of floating, which is static equilibrium. Sinking is not static equilibrium. Neither is the opposite of sinking. Is there a word for what happens when something rises in a fluid? Yeah, not when it, so floating is usually reserved for at the interface. Technically, submarines float, right? But like when so we say something is sinking when it's getting deeper and deeper and deeper. I guess the word is rising, right? Elevating. Technically true, but there are no elevators in water. That'd be cool. There are some, like the handicap elevators to get people in and out of pools.
Isn't the buoyant force equal to the weight of the liquid?
Water displaced, yes.
That's not true for a floating object.
It's still true. It's true whether the object's floating or sinking. The buoyant force is always equal to the weight of the water displaced by the object. Whether or not that buoyant force is big enough to counteract the object's weight, that's when you know. That's how you determine floating or sinking. But the buoyant force is always the weight of the water displaced. For both, it's going to be exactly equal to the boat's weight. Again, I know because boats are supposed to be on the surface of water. That's asking a great question. That's a good question. Yes.
In chapter 14, like in the Bernoulli's equation,
Hmm.
when do you use like A1 times B1?
The equation of continuity. So the question is, when it comes to Bernoulli's equation, when or how or what, where does the equation of continuity come into play? Oh, that's supposed to be P. So V2 squared plus rho GH2. All right. They kind of, these two come together as a package usually because they both are involved in fluid flow. So you'll notice Bernoulli's equation doesn't care about the diameter of your pipe. Bernoulli's equation only cares about how fast fluids are going and if there is any elevation change for that fluid. If your pipe changes its diameter, that's equation of continuity. Right? You can use the equation of continuity to solve for a relationship between, say, V2 and V1. Right? And so these two equations can help each other out. But to answer your question, Kyle, it's if your pipe changes its diameter, that's equation of continuity. If the pipe changes its height, right? If the fluid, not just a pipe, just any fluid goes up or down, that's Bernoulli's equation.
So, if like you give us the velocity in a pipe that changes its height, we would just plug it into the first side and get our secondary velocity, and then we can plug both of them. The velocity you gave us on the first half of the velocity we figured out.
Sure. Assuming you know the pressure differences. There's really three things you got to keep track of in Bernoulli's equation, right? It's pressure, it's height, and it's speed. The equation of continuity tells us that we can't make water out of nothing, right? If water's flowing down a pipe, the flow rate has to stay consistent. It's a conservation principle, if you will.
And when do we use absolute pressure? Like in
Yes.
equation, do we use absolute pressure?
Always. I mean, for physicists, pressure is always absolute pressure. We might read gauge pressure, but we will often just convert it into absolute pressure. The answer is you always use absolute pressure. So chemists will get all bent out of shape for me saying that, because they use gauge pressure in a lot of their stuff. But for them, they're just working at atmospheric pressure anyway, so what, why does it matter? Well, physicists, we're not always working at atmospheric pressure. Space, we're under the water, we're doing, all kinds of different things. But yeah, absolute pressure is always the safest bet. What do you say?
When do we use orbital velocity and circular velocity?
Okay. Did you have a question about fluids?
Yeah.
Okay, so we'll do this one and then we'll get to gravity.
On our equation, when we have like the siphon that's going into the tube and out of the tube,
Mhm.
we cancel them out because the atmospheric pressure is both
Right.
the same, right?
Right. And when I did the siphon problem, it was the pressure at the top,
Yeah.
level of fluid of the water, and then it was the pressure as the water exited,
Yeah.
right? The water has exited the tube, so it's at atmospheric pressure. The water up here is at atmospheric pressure, so it cancels out. If, however, I said, what's the pressure inside the end of the tube right before the water comes out, that's not atmospheric pressure anymore. Okay, orbits and orbital velocity. What was your question again? How do you tell the difference between what and what? Orbital speed and circular motion? You don't? They're the same thing? I'm not sure I understand. And maybe it's just because I'm a physicist and I've done this for a while. So if we got the Earth and we've got something in orbit around the Earth, we have the orbital velocity equation. Is that what you're asking about? So velocity of orbit is GM over R? That was a guess. Okay. How do I tell the difference between this and?
Or like when do you use circular motion when dealing with orbits?
So the end. So when do you use circular motion when dealing with orbits? The answer is yes. An orbit is circular motion. So while this equation we came up with in chapter 13 is written in terms of like big G, right, and the mass of the planet and all this kind of stuff, this still applies because it's still circular motion, right? So what V would I put in there for this circle? It's this V right here, right? Those two V's are the same. Remember, the V in the centripetal acceleration question is the tangential velocity. Well, that's what orbital velocity is. It's the tangential velocity of the object. So when we do V is equal to 2 pi r over the period, okay, well, it's the same V. We can apply all of our rotational dynamics, kinematics, everything to orbits to find out whatever we want. But we usually don't talk about orbits in terms of like angular speed or delta thetas that we do. Not usually real concerned about what the centripetal acceleration is of that orbit. We could go find it, it's fine, but orbital mechanics kind of pushes all of that to the side and goes straight for, well, it's really kind of crazy. These orbits only depend on the mass of the planet you're orbiting and how far away from the planet you are, right? Did that answer your question? Yeah. To me, it all is the same. It's just orbital mechanics makes it faster. It's a shortcut, so I don't have to keep going through all of that orbital kinematic or rotational kinematics. I can skip the rotational kinematic and go straight to this. Again, I think you saw that. Maybe you didn't realize it, but when we did energy, like the energy of an orbit, and I rewrote kinetic energy as something that looks completely different, right? That was all in an effort to not have to write 1/2 mv squared all the time, right? I wanted to write it in terms of things that are natural for orbital mechanics, which are big G, big M, and how far away. Those are like the three things that dictate orbital mechanics.
Are you gonna give us the equations for like big G, Earth's radius, and stuff like that?
So I never give an equation, because I expect you guys to put those, but like the constants, the numbers, yes. I will always give you those constants. Even if I've forgotten to put it on the exam, you just come up and ask me and I'll write it on the board. Some of my physics 4C students came up yesterday doing their test. What's the mass of an electron? It's like, I could tell you, but you don't need it for that problem. And the look on their faces was like, right? And I'd pull them back. I was like, here it is. You can have it. But the hint is, you don't need it. I'm not sure I was being nice or mean in that moment.
That's like giving someone a key to a car that doesn't exist.
Right.
That was a hard exam.
What's that?
They said it was a hard exam.
They said it was hard? Yeah. It could have been a lot harder. It was relativity, quantum mechanics, and nuclear physics in 12 questions. I need about 36 questions just to begin scratching the surface of those topics. But anyway, we do what we must. My physics 2A students next semester are only going to have 7 questions on their exams. Because the way the class is taught, we give them the exams in lecture, not in the labs. So they only have, well, an hour and 15 minutes instead of 2 hours. So they do 7 questions instead of 12.
Not much room there.
So it's been like, I don't know, 6-7 years since I taught this class. And I have no memory of anything that happened before the pandemic. So I think what I'm going to do is I'm going to do like a hard rubric on, if you get the problem correct, that's 1 point. If you've got the setup correct but failed the math, that's half a point. So effectively, there's 14 points available for them, right? Anyway, it's going to be, oh, and they also have 5 exams, not 4. Because they actually have 5 units of information in physics. 2A is like, 2A and 2B, you take all of physics 4 ABC and you squish it into 2 semesters. And then you hand it to all of these people that want to be like doctors and nurses and things like that. So number one, they don't want to be taking physics in the first place, otherwise they wouldn't have been a biology major. And second of all, we're taking all the physics and cramming it into 2 semesters. It's like, it's definitely the harder of the 2 classes. I think. You guys have it easy. You get 3 semesters. Well, that's not easy. You're right, it isn't. But, yeah.
Can you go over the idea of Newton's cannonball, like orbiting?
Shoot something fast enough sideways, and by the time it falls, the ground will have curved away beneath it. That's Newton's cannonball. That's an orbit. Newton's cannonball only works if you have a curved surface. So if you're harboring any flat Earth ideas.
Could you draw that out, how that would look like Earth
So, the International Space Station here, as I've so accurately drawn, right, has a tangential velocity, right, okay, and it's got gravity pulling it down, right? So it's in free fall, right? It's falling, right? It's just that by the time that it gets, say, over here, right, it's fallen, it's changed its height, but the ground has also changed its height. If you have a flat surface and you have a force of gravity pulling down, then in the next instant, this thing is going to be closer. But what happens if we do exactly the same drop, only instead of a flat surface, you do something like that? The heights here are exactly the same. That's Newton's cannonball.
And why does the height of the Earth change? Is it because of it being pulled?
Because we live on a spherical surface. Surface of the Earth isn't flat, it's round. It's curved.
So it has nothing to do with it being pulled by the sun?
Nope.
Because of gravity now?
I mean, Earth is round because gravity pulls everything inwards. And so the stasis between gravity pulling all of the Earth's mass together and that mass kind of pushing away gives us that circular shape. Things that aren't massive enough, like lots of asteroids and things, they aren't spherical. There isn't enough gravity to sort of push them around into that shape. But once you get to a certain mass, it is, circularization begins to happen. It's a natural outcome, which is why stars are spheres. Now, I should point out that the Earth is not a perfect sphere. Okay, does anybody know what the shape of the Earth is? It's an oblate spheroid is the name of the shape. The Earth is middle-aged, which means it's bigger around the waist. Okay, so at the equator, it bulges out slightly, partially because of its rotation. Okay, but and so north and south poles are like sort of squished on. It's called an oblate spheroid, but it is so close to spherical that it would be very difficult for you to if you're standing looking at back at the Earth from the moon, you would say it's round. So the sun's an oblate spheroid. Most planets are oblate spheroids because they're just a little bit squished because of their rotation axes. Did that answer your question?
Yeah, that's it.
Okay.
Have you rounded flat earthers in the class before?
Mm-hmm.
Rounded flat earthers.
Yeah, I kicked them out.
Right.
No. So, yeah, so the flat Earth movement, the flat Earth society, that physicists are partially to blame for that, because that was a joke that was started in the early 1970s, University of Arizona at Tucson. And the joke, oh, you remember the Flat Earth Society? That was the joke, right? Because everybody knew it was a joke. The problem is with the internet, people started taking it seriously. And the internet breeds conspiracy theory and all kinds of stuff, right? And now it's become like a legitimate thing, right? And it doesn't help when a physicist arrogantly says, well, they're stupid, right? We should be communicating with these people, not ridiculing them. Right? Because they honestly believe, I've run into people that honestly believe that, right? In spite of all the evidence. And the sad part is, we live in, what are they calling it now? A post-truth society, where facts don't matter anymore. All that matters is what I believe.
That's how you feel.
Okay, right? You can believe the sky is green, but it's not. Right? You can disbelieve in gravity, but you still have to obey. Like there are absolute truths that exist. No amount of wanting it to be different is going to change that. So, as a physicist, right? I study those absolute truths every day. I teach them to. This is the way things are. as a person of faith who's very active in his church and belief system, I'm grateful that I have a belief that doesn't contradict any of that. So, you know, when those two things, faith and science, are in conflict, then both are wrong somewhere, somehow. Our understanding of it is flawed. So, and that to me is exciting, because now we can go discover stuff, right? But you can't have a closed mind. You can't just sit there and say, well, my way is the right way. No.
Be careful, you're gonna get canceled.
Me? Cancel away. I have Newton on my side. Before you go, in the last 2 minutes here, I want to thank you for a fantastic semester. You really have been a great class to be with. Normally, I would say see you after the summer, but as you know, I'm not teaching Physics 4B or 4C next year. I'll be with the Physics 2 students. I am leaving you in excellent hands. Dr. Crowfoot, Mr. Ragsdale, Dr. Trelawney, or Mr. Trelawney, they're all excellent teachers. We all work together very tightly behind the scenes. We're always talking about you. I will be spying on you as you go through those classes, just making sure that you're being well taken care of, but I really don't have to worry. I hope that something has been a benefit to you in this semester. And I'm not talking about the physics. You'll go on and either use or not use anything that you've been taught in terms of physics in here. What I do hope is that you have learned how to learn, that you've learned to believe in yourself, that you can do it, and that it's worth doing. So thank you very much for a great semester. I will see you tomorrow, right, for that exam. When are we meeting for the exam autopsy? Wednesday. Yeah. I'll get several of you wandering in. What is going on this week? It's next Wednesday. When? At 8 o'clock. Where? In this room. Okay. 3 of you will still show up on Thursday. That's all right. See you tomorrow.
You still have your 4B.
Yeah, I'm gonna leave all that up.